Hello guys, this is Rakesh from Bodhee Prep, and in this video we'll extend the logic of progression. In the last video we have gone through the arithmetic progression. In this video we'll understand the basics of geometric progression, which is another very important progression for CAT exams, right? So let us understand what is geometric progression. So I'll give you a simple formula for it, and we'll also discuss the formula, and we'll also find the nth term, the sum of n terms, etc. The same thing what we have done for the arithmetic progression. So unlike arithmetic progression, wherein the every next term has some addition or subtraction of the previous sum, that term is a common. In geometric progression, things are not added, rather it is getting multiplied, right? So if I take, say, two numbers, say I'm taking a number 4 and another number 16, and somebody asks me to find the geometric mean of it, right? So I'm using a formula to find the geometric mean, right? So for two numbers, the geometric mean of these two numbers would be the under root of their product, right? The under root of their product. Since there are two terms, so we'll be taking under root and we'll be taking the product of it. We'll be taking product of it and then we'll be taking the under root of it, right? So of course, this is equal to under root of 64, which comes out to be 8. So 8 becomes the geometric mean of 4 and 16, right? Certain things which are property which we can just observe. For example, this number 8 is lying between the smallest and the largest number for which we are finding the geometric mean, right? Apart from that, we always find the geometric mean for the positive numbers. And whatever the under root we take, we only retain the positive number. So we are only talking about the positive integers, or not specifically integer, positive real number, I would say, right? It could be any real number. Positive real number, for positive real number, we find the geometric mean, right? So what is the formula? What is the formula to find the geometric mean for any given n numbers? So before I reach to the formula, let me give one more example. Suppose we have three terms. Say the terms are 2, 8, and 32, and we have been asked about to find the geometric mean of it. So the geometric mean for these three terms would be what? The cube root of their product, right? Here, there were two terms, so we were taking the square root of their product. Here, there are three terms, so we are taking the cube root of their product. So if we find, then it will be the cube root of 512, which on calculation, I'll be getting 8 again. So 8 becomes the geometric mean of these three numbers. So if I extend this particular logic, we can say that if I have, say, four number A, B, C, and D, and we want to find the geometric mean of this, then of course, it would be the fourth root of their product, right? Whatever the positive value A, B, C, D is. So we can extend this logic to create the formula, and that formula is for n terms, say A1, A2, A3, etc. till an. For n terms, if I want to find the geometric mean, then the formula is we have to take the nth root of their product. So we'll be just multiplying each of these product, each of these number, and we'll take the nth root of it. So this is the formula to find the geometric mean of any number or any n numbers. All numbers have to be a positive. Fair enough, right? So here the things are getting multiplied. Now, what about the general terms? If I want to find or the nth term. So specifically what we do is that geometric mean, if I take numbers, say 1, 2, 4, 8, 16, this is a series, which I say that this is in a geometric progression. This series is in a geometric progression. Now, why this is in a geometric progression? The reason being that every term, and I take the previous term, immediately previous term, and if I take the ratio of it, so if I take 2, I have to divide it with the previous term. The overall value would be 2. If I take the next term, and if I divide it with the just previous term, the overall simplification of this will again give me 2, right? 4 divided by 2 is 2. The same thing you can see will appear for every term like this, right? We can just continue. Every time the overall value is 2. So what is happening here is that here the ratios is common. Here the ratio is common. And what is the common ratio? 2 itself. What is the common ratio? 2 itself, right? So if I want to make it in a general form, then what I can do is that if there is a term A, then the next term should be such that if I divide this term with this, I should be getting a common term. So the next term here would be what? AR square. As you can see, if I divide AR with A, I'll be getting R. So this becomes what? Common ratio. So this term divided by this should also give me R. So what I should be doing is that I should be taking it as AR square. When divided by AR, again, I'll be getting R. So what is happening is that we are effectively multiplying R to the every next term which is appearing. So the next term here would be this. The next term here would be this. How many terms I have written? Let us count them. I have written 1, 2, 3, 4, 5, and 6. This is called the first term, right? This R is called the common ratio, right? This is the second term. This is the third term. This is the fourth term, so on and so forth. So effectively here, if I just observe, then the power of R is 5, but the term number is the sixth term, as you can see. So if I extend this logic and apply a common sense, then I can say that if I want to find the nth term, then it should be A multiplied by R to the power n minus 1. The power should be 1 less than the term number. If I'm finding the nth term, it should be A into R to the power n minus 1. Why so? Because the first term, the power of R is 0, right? In the second term, the power of R is 1. In the third term, the power of R is 2. So nth term, the power of R would be 1 less than the term number. Fair enough, right? So this value is called the nth term. This is called the first term. R is the common ratio, right? This is the geometric progression. And how do we find geometric mean of any given numbers? This is the formula which we'll be using it, right? So I have introduced the geometric mean formula first. Then I have made you understand what is geometric progression, right? You can do the reverse of it also. You can understand geometric progression first, and then you can go for the geometric mean formula. It doesn't matter because we have to use specifically geometric mean formula a lot, right? So we have done the nth term, correct? So let us take some examples based on the nth term. So for example, if I have a geometric progression which is say 5, 25, 125, so and so forth, right? This is 125. And I want to find that which number will be the 10th term. So what we can do here is that we can compare this geometric progression with this. This is a generic form. So the first term obviously is 5, right? This 25 can be written as 5 into 5 to the power 1. This can be written as 5 into 5 to the power 2, as you can see, correct? Extending this, we can see that the value of R would be equal to 5 itself. How do I find the value of R? Straight away by comparison. This is the first term. So here A is the first term. So the value of R would be 5. We can cross verify that here also the value of A is 5 and the value of R has to be 5, so that it should become 5 squared, the third term, right? Just by comparison we can find, or what we can do is that we can divide the second term with the first term to get the ratio. Again, we can divide the third term with the second term to specify or to cross check whether we are getting the same ratio or not, right? So we have got the first term which is R, the common ratio is also R. The 10th term, as per the formula, if I want to find the nth term of this, then it should be A to the power n minus 1. Now the value of n has to be 10. So the 10th term would be equal to 5 into 5 to the power 10 minus 1, which effectively is 5 into 5 to the power 9, which effectively is nothing but 5 to the power 10. This becomes the 10th term, right? And it's quite easy. You can see that if I convert every term of this to the power of 5, then the first would be 5 to the power 1, the second would be 5 to the power 2, the third would be 5 to the power 3, so on and so forth. So we can see that the 10th term has to be 5 to the power 10. Why? So because the first term has the power of 1, the second term has a power of 2 over 5, the third term has a power of 3 over 5, so on and so forth. So the 10th term would be 5 to the power 10. Fair enough, right? Okay. Now let us take more examples. So I'm writing a geometric mean, which is 2, 8, 32, right? This is going on till some number of terms. And we have to find that which term will be equal to 131072, right? We don't know which term this number will appear. So what we can assume is that, let us assume that this is the nth term. So first of all, we have to find the first term. First term is quite obvious. The very first term is equal to A. What is the common ratio? The common ratio is 8 divided by 2, which is 4. To cross check, we can see that 32 divided by 8 is again 4. So the value of R is 4. We have found the A first term and we have found the common ratio. So what is the nth term? The nth term is a into r to the power n minus 1. And we are assuming that this is the nth term. So let us assume that this is equal to 131072, right? Let us substitute the value of n. Substitute the value of a and r. So the value of a will be 2. The value of r would be 4 to the power n minus 1. Correct? And that is equal to 131072. So 4 to the power n minus 1 would be this divided by 2. So I'll take the help of calculator here. So 131072 divided by 2, I'll be getting it 65536. Correct? Now this again would be some power of 4. So what we can do is that we can take help of calculator or some other advanced method to figure out, right? So here, if I take help, then this is effectively equal to 4 to the power 8. So on comparison, we can see that the base is same. So the power must also be same. So the value of n minus 1 should be equal to 8, which gives me that the value of n should be equal to 9, right? So this is the ninth term of this particular series. If I extend this series, write all the terms, then on the ninth term, I'll be getting 131072. Fair enough, right? Okay, let's take more examples. Now it is another geometric series which starts with 1, then the next term is 1 by 2, the next term is 1 by 4, then the next term is 1 by 8, so on and so forth. Clearly, you can see that every coming term is getting half of the previous term, right? So the common ratio would be what? 1 by 2. We can check this divided by 1 is 1 by 2. 1 by 4 divided by 1 by 2 again is equal to 1 by 2. You can verify that 1 by 4 divided by 1 by 2. So I can write it as 1 by 4 multiplied by 2, 2 by 1, which comes out to be again 1 by 2. So here the first term is a and the common ratio is 1 by 2. Suppose we want to find what is the seventh term. For example, what is the seventh term of this particular series? So we clearly know that we'll assume that the nth term will be in the form of a into r to the power n minus 1, where in this case the value of r would be what? 7. So the seventh term will be equal to a into r to the power 6. We can substitute the value of n to be 7. The value of a is 1 and the value of r is 1 by 2. So clearly we can substitute here. So it will be 1 into 1 by 2 whole to the power 6, or 1 divided by 2 to the power 6. We can calculate it. So it will be 1 over 2 to the power 6 is how much? It is 64, right? 2 to the power 5 is 32. So 2 to the power 6 would be 1 by 64. So 1 by 64 is the seventh term of this particular series, right? We can create the pattern also. I can write the first term as this. The second term would be 2 to the power 1. The third term would be 1 upon 2 to the power 2, as you can see. That the fourth term would be 1 over 2 to the power 3. So the fifth term would be this much. Sixth term would be this much. And the seventh term is this much, as you can see, right? So either we can use the formula or we can extend this logic. Using the formula is recommended because this is a simpler example. So you can write both the things. At times what happens is that the questions or the terms are a bit complicated. So always use the formula. But for using the formula, you should be very much clear that what is the first term and what is the common ratio. Then only you should be applying this formula, right? Okay. So this is the formula for finding the nth term. Now let us focus on finding the sum of n terms, like similar to what we have done in the arithmetic progression. So if I take the first term, which is a, the second term to be ar, the third term to be ar square, then ar cube, so and so forth, till the nth term, which is ar to the power n minus 1. and we want the summation of all these terms. So I'm just writing the some terms which are at the end. So n minus 1th term would be this much and the nth term would be this much. Let us assume that this is equal to Sn, which is the sum of first n terms in in geometric progression. What I'm doing here is that I'm deriving a formula so that if I know the formula, I get the value of a, r, and n. We can directly substitute there and we can get the sum of any geometric mean, or any geometric progression. So what I'm doing here is that I'm multiplying this with the common ratio. I'm multiplying this equation with common ratio. What is the common ratio here? R. So let me multiply. So it will be what? R into S of n, right? This will make it A into R. So I'm writing it just beneath this. The second term will be multiplied. Each of the term will be multiplied with R. So this term will multiplied with R. I'll be getting AR square. This term when multiplied by R, I'll be getting AR cube, so and so forth. Right? Here, I'll be getting at last, it would be AR n minus 1 because this thing when multiplied by R, I'll be getting this. And this when multiplied by R, I'll be getting AR to the power n. Right? Now what I'm doing is that I'm looking at these terms, I can see that many terms are common in both these equations. So let me subtract it so that the common terms should get vanished. So I'm subtracting this with this, right? So I'm doing S of n minus R times of S of n. This is what I'm doing. So effectively, these things are getting subtracted with this, right? So here we can see that these terms, they are like terms, so they will get cancelled. In fact, this will also get cancelled with the previous term, which is ARn minus 2. So this will also get cancelled. This will also get cancelled. So what effectively we are left is the first term and the last term of the second equation. Rest every term will get cancelled. So I'll be getting A minus A into R to the power n. Right? Here again, since I'm interested in finding the sum of n terms, so let us take Sn common. So here it will be 1 minus R. Here A is common, so I'll be getting A 1 minus R to the power n. So S of n effectively is what? A 1 minus R to the power n divided by 1 minus R. So this becomes my formula for finding the sum of n terms. Correct? In some of the books, what you'll be finding is that the sum of n terms is given as A R to the power n minus 1 over R minus 1. Both are correct because what we have done is that we have just switched Rn and 1 in both numerator and denominator. So it will not make any difference, right? So you can use both the formula. Either you can use this formula or you can use this formula. It doesn't matter. Fair enough, right? So let us take some examples how to use this sum of n terms. So I'm writing this, let me just check. So suppose the terms are 1, 2 by 3, 4 by 9, so and so forth, right? We have to find the sum till 5 terms, right? So what we can do is that clearly we have to first of all identify whether this is geometric mean or not. So this divided by 1 is 2 by 3. Is this divided by 2 by 3? 2 by 3. Let's see. So 4 by 9 divided by 2 by 3. Again, we can change division and convert it into multiplication. So it will be 3 by 2. Clearly, this comes out to be 2 by 3. So this is in a geometric progression where the value of A is 1 and the value of R is the common ratio. We have to add till the 5 terms. So S of n terms, as for the formula is what? A 1 minus R to the power n divided by 1 minus R, right? We can substitute. So S of 5th term would be what? The value of A is 1. 1 minus R is 2 by 3 to the power 5 divided by 1 minus 2 by 3. Right? Now this we have to simplify to get into a rational number, right? So I'm just leaving that simplification process and you'll find that the overall answer would be 211 divided by 81. This would be the sum of the first 5 terms, right? So what we have understood what is geometric progression. We have understood what do you mean by geometric mean, right? Or how to calculate the geometric mean. We have also understood that what is the nth term, how do we find the nth term of geometric mean, and we have also derived the formula for finding the sum of first n terms of any geometric mean, right? There is one very important formula for sum of geometric mean apart from this, which is sum of a series which has infinite terms, right? So this is a very, very interesting and specific case. We have infinite terms and we can add it to get a finite value in a geometric mean, but there is certain condition for it, right? So let me take one of those conditions and try to understand it. 1, 1 by 2, 1 by 4, 1 by 8. This is in a geometric progression, right? What if I ask you, what will be the sum of this series till infinite? So I'm adding this. Again, next term would be 1 by 64, sorry, 1 by 16. Then 1 by 32, so and so forth till infinity, right? Will never stop somewhere. It will go till infinity. Now, if we closely observe them, forget about the formula for the time being. If we closely observe it, then what we are finding is that every next term is half of the previous term. Or we can say that every next term is smaller than the previous term, right? So this is the highest term among all those infinite terms. This will be the second highest term among all those infinite terms, so and so forth. So what is happening here is that the value of the upcoming terms will keep on reducing, right? So our term, there'll be a time wherein these terms will keep on getting very close to zero, right? We can almost assume those terms the value to be zero because it will be 0.000000 something like that till infinity and then some specific small number. So overall their effective value will remain zero, right? So what we can do here is that we can apply the formula. Let us assume that till nth term, if I want to add, then sum of n terms would be what? As per the formula, the value of a is 1 here, the value of r is 1 by 2 here. So here the formula, as per the formula, it is a, so a is 1 only. 1 minus 1 by 2 whole to the power infinity divided by 1 minus 1 by 2. Fair enough? Now just assume that 1 by 2 to the power n, and if n tends to infinity, right? Although the derivation here involve calculus, etc. I'm not going into that, but I want to get this value by using common sense. If the value of n is very high, for example, if the value of n is 1 crore kind of thing, you can just imagine this overall value would be very, very negligible, almost zero, right? Here I'm just taking 1 crore. You can assume that crore kind of thing. Then overall this value would be too negligible to be ignored, right? Almost close to zero. So what we can do is that if the value of n is tending till infinity, we can just assume it that it is so negligible to be ignored. So overall, the value would be what? 1 divided by 1 minus 1 by 2. On resolving it, we'll be getting it as 1 divided by 1 by 2, which comes out to be 2. So 2 is the sum of this series if I'm adding it till infinity, right? So if I can modify this formula, that sum of infinity would be given as a over 1 minus r, because r to the power n is very negligible. So this become my sum of infinity formula. But as I said that this formula can never be used everywhere, right? This formula has to be used for a specific reason, specific cases. And that case is that the common ratio has to be less than 1 and greater than minus 1. If the common ratio on a number line lie between minus 1 and 1 in this area only, then only we can find the sum of infinity term, which will come as a some finite number. For example, 2 is a finite number, right? Some value. Otherwise, we will never be using it. It will, in other cases, for example, if r is greater than 1 or less than minus 1, in that case, what will happen is that the infinite sum will tends to either positive infinity or negative infinity, right? So since infinity is of no value to us, so what happens is that if there is a question which is asking about sum till infinity, 99.99% cases, this should be the common ratio, or the common ratio should lie between these two, then only we can find it, right? So this is sum of infinite terms. I hope you have got this formula also. So let us take one more example. Suppose we want to add 1, 1 by 2, say 1 by 3, then 1 by 9, then 1 by 27, so and so forth, right? We want to add it till infinity. right? So here the value of a is 1 and the value of r we can see is 1 by 3. Is 1 by 3 between -1 and 1? Yes, because 1 by 3 is lying between 0 and 1. So obviously it will lie between -1 and 1, right? -1 is here, 1 is here, 0 is here. So 1 by 3 will be somewhere here, correct? So it is lying between it, correct? So sum till infinity would be what? As per the formula, it is a over 1 minus r. So it will be what? 1 over 1 minus 1 by 3, right? So if you solve, we'll be getting it as 3 by 2. We'll be getting it as 3 by 2. So 3 by 2 is the sum of this value, right? It has a very practical use. For example, this particular thing can appear in geometry also, right? Let's have an example with a geometry. So understand the question clearly. Here, suppose there is a square given. There is a square given. We all know that. I'm assuming that you all know that what is the area of a square. If the side is a, right? The area of the square is nothing but a square, correct? If I take the midpoint of each of these sides, if I take the midpoint of each of this side, then, and I add this midpoint. So by symmetry, we can also say that the figure so formed in between is also a square, right? But what is the side of this square? What is the side of this square? Or what is the area of this square? If I apply a simple common sense, then I can say that the area of this smaller square has to be half of the area of the larger square. How? If I just flip this will cover this much. If I flip this will cover this much. If I flip this will cover this much. If I flip this will cover this much. So what is happening is that the outer portion area is covering the inner portion area, right? So the larger square is the area of the larger square is included both inside and outside, right? And inside square area is equal to area of the outer side. So we can say that area of the larger square, if this is a square, then the area of the inner square would be half of it. Fair enough, right? And if I repeat this, that I take the midpoint of now the smaller square, and if I again join this point, again I'll be getting a square. So this square, from the same logic, I can say will have an area which is half of this smaller square. So the area of the smaller square is this. So the area of the smallest square till now would be what? Half of it, which is equal to a square divided by 2. Again, has to be multiplied by half. So it will be a square divided by 4. This process will be repeated infinitely. This process will be repeated infinitely. And we have to find the sum of the area of all these infinite squares of form, right? So what we can do is that, and assuming that the area of this, so say the side of this square is say 2, fine. So area of the largest square would be what? 2 square. The area of the square which is just inside this largest square would be half of it. So it will be 2 to the power 1, 2 square divided by 2. Then again inside the inner square, it will be 2 to the power 1 divided by 2. So it will be 2 to the power 0. Then 2 to the power -1. Then 2 to the power -2. So and so forth till infinity. So we have to add it. If you closely observe that this is a geometric progression, why? Because this divided by this, 2 to the power 1 divided by 2 square is half. This divided by this, 2 to the power 0 is 1, divided by 2 to the power 1 is again half. So we have identified that this is the common, this is the first term. The common ratio R would be 1 by 2, which is lying between -1 and 1. And we have to add till infinity. So we can apply the formula that sum till infinity for these terms would be what? A, which is 2 to the power 2 divided by 1 minus 1 by 2, which comes out to be 2 to the power 2 into 2, which is nothing but equal to 8. So if I add all the areas of these square till infinity, the overall sum will be 8 or close to 8. Right? So these are the three formulas and terms which you have to understand, right? Geometric mean formula, the nth term of the geometric mean, sum of n terms, and within sum of n terms, we have to find we have to know the specific case wherein we have to add the series till infinity. For that, the binding condition is that the common ratio should be between -1 and 1, right? So in the next class, I'll be taking some question from both arithmetic progression and geometric progression, and also help you to understand there is certain series which is called arithmetic and geometric, combination of arithmetic and geometric progression also, right? So we'll see those interesting cases.